couple pictures now, and I want to point out some similarities, a little bit of difference, but mostly similarities between the pictures here. First, I want to take you back to something that we did in Physics 20. It's a hill with a car on the top of the hill. It's one of those roller coaster type problems. If you saw this question in Physics 20, say, want to find the speed of the car when it reached the bottom of the hill, what would you do? What would you do? You make it? Yeah, we do EI equals EF. Good. It's exactly what you do. EI equals EF. Let's say that it starts at rest up here, and it's got a height of, let's say, 20 meters. And again, we're looking for the speed at the bottom here. How would this look? Well, EI would be, what kind of energy would it have? There's potential energy, gravitational potential energy, because there's a height, mgh. Would there be kinetic energy at the top of the hill? No, there wouldn't, Peter, because there's no speed. It's not moving. Good. And what kind of energy, Peter, do we have at the bottom of the hill? No, at the bottom of the hill, we have all kinetic energy, right? Why don't we have any potential at the bottom of the hill? Yeah. Listen, the bottom of the hill, Peter, the bottom of the hill is the bottom of the hill. We're defining that as our 0 point, which means from that point, there is no height. And if there's no height, there's no potential to go any further. So we're going to say at the bottom of the hill, it's just kinetic energy. Does that make sense, guys? That's a Physics 20 problem, and we could solve that easily with a little bit of review. We could solve that quite easily, I think. Now, I want to show you another picture now, though. This time, instead of having a car at the top of the hill accelerating down the hill because of a gravitational field, right, 9.81 meters per second squared, this time we've got two charged plates, or we established the other day that we don't actually have to have charged plates. We can have things that are like charged plates, right? The cloud and the earth, top part of bumper cars versus the bottom. Okay, things that are like charged plates. Top one's going to be positive, bottom is going to be negative. This time, there's an electric field pointing downwards instead of a gravitational field pointing downwards. And this time, instead of having a car at the top of the hill, we have a charged particle that's positive at the top of the hill or at the one side of the plates. Now, what happens to this car as it starts going down the hill? It speeds up because it's attracted towards the bottom of the hill. What happens to this positive particle? It gets attracted to the bottom plate, or it goes in the direction of the electric field, which means it speeds up. It accelerates, right? Just like the car accelerates down the hill, this charged particle accelerates through the electric field. One accelerates through a gravitational field, one accelerates through the electric field. We've talked all unit about the similarities between electricity and gravity, right? This is no different. We're going to analyze this in exactly the same way. We're going to say EI equals EF. What kind of energy does it have at the beginning here? Okay, is it a no? I thought you just said it. No? All right, I thought you said it. No. If it's potential, yeah. If it's going to speed up to the other plate, something has to cause it to speed up. That's potential energy. But this time it's not gravitational potential energy. It's electric potential energy. Hey, in Friday and earlier today, we established what electric potential energy is, right? This was potential. So potential energy is this. What we're going to do instead of subbing in MGH is we're going to sub in QV. Not gravitational potential, but electric potential. What kind of energy does it have when it reaches the other side, Evelyn? When it gets down here? Yeah, it's moving. It's got kinetic energy. Good. What happens if we change this up a little bit? What happens if this car at the top of the hill is given an initial speed of 10 meters per second? How does that change things now? Yeah. Yeah. So we've got both potential and kinetic on the left-hand side, right? Still, at the end of it, we've still got just kinetic energy, right? Because it's moving, but there's no height at the end of it. What if I give this charged particle an initial speed? Typically, it wouldn't be something like 10 meters per second, but maybe 10,000 meters per second. How does it change things? It's the same thing, right? Potential plus kinetic equals kinetic energy at the end. What if I didn't want to find the speed at the end of the problem? What if I wanted to find the speed right here, halfway down? Doesn't change anything at the beginning, right? How does it change my final equation? For speed, you mean? No, that's a good guess, actually, but it wouldn't work because v is squared. It's not a linear relationship there, but it's a good guess. Yep. Yeah, look, there's kinetic and potential energy at the beginning because it's moving and there's a height. But now at the end of the problem, it's moving and there's a height. So there would be potential energy right there as well. What would the initial height be? 20 meters, right? What would the final height be? Because it's moved through a height of 10 meters. What about over here? Let's say the potential difference between here is 20 volts. Let's say I wanted to find the speed as it's gone halfway across. The initial doesn't change. How does the final change? Kinetic energy and potential. What's the potential energy at the end? QV instead of mgh. What was the initial potential? 20. What's the final potential? 10. Isn't it the same thing? Listen, I don't know about you, but when I have a charged particle, when I see a question with a charged particle accelerating, I have a tough time visualizing the charged particle accelerating. I do not have a tough time visualizing a car rolling down a hill. Okay, I can picture that. I can see that. I can see the details. I can see the rust on the back bumper of the car. Two people in the car. One of them's texting. Oh, wait, they're both texting. I can see it. I can see what's happening. So when I get a question where a charged particle is accelerating, then I automatically start thinking about a car going down a hill. And then I start writing it out like I would have in Physics 20, this side. And then what do? Well, I replace mgh wherever it appears with QV. mgh initial equals QV initial. mgh final equals QV final. Otherwise, it's exactly the same thing, right? Now, what would happen, just out of curiosity here, what would happen if the car was given an initial speed of 10 meters per second? It was going up the hill. It reaches the top, and it just barely makes it to the top. And I was looking for the height that it went up. How would I solve that problem? Christian? Almost. It would be the same thing, but not negative. Yep. Yeah, pretty much just flipped, right? What kind of energy do I have at the beginning of this problem? Kinetic energy, right? Because it's moving. 1/2 mv initial squared. No potential at that point. What kind do I have at the end? Well, it's not moving. It stops, right, when it reaches the top. But I've got potential at that point, and I just solve for the final height, right? Agree? That's a Physics 20 problem again, right? And in Physics 20, you could have solved that. Yesterday, you couldn't have solved that because it's been a year since you've done it. But now it's probably starting to come back. At least I hope that it is. But what if I have, let's switch it around a little bit. Now my plates are vertical. Now this is a positive plate, this is a negative plate. Let's say that I've got a negative particle going this way with a speed of 10,000 meters per second. And I want to know what the potential difference is across those plates. What's going to happen to this charged particle as it goes through that potential difference? Speed up or slow down? Slow down, right? Because it's repelled by the negative plate. It slows down, just like this car as it's going up the hill. slows down. When I see a charged particle speeding up, I want you to think of it as a car going down a hill. When you see a charged particle slowing down, I want you to think of it as a car going up the hill. I don't care whether the charged particle is going left, right, up, down, diagonal. I don't care about that. If it's slowing down, I want you to think of it as a car going up the hill. Okay, close your eyes, and I want you to picture the car going up the hill. At the bottom of the hill, what kind of energy does the car have? What kind of energy does a car have at the bottom of the hill? It's got kinetic. So I'm going to write that in. At the top of the hill, what kind of energy does the car have? Potential. But I'm not going to write in MGH this time because it's not gravitational potential. I'm going to write in QV because it's electric potential. Do you see how this question is identical to this one except for this? And do you see how this question is identical to this one except for, once again, subbing in QV wherever we have MGH? You got it? All right. I'm going to do an example here. Okay. Listen. In summary, charged particle speeding up. It's like a car going down a hill. If I could just learn how to spell going, then it would all be good. There we go. Going downhill. The charge is slowing down. That's like a car going up the hill. In both cases, it's EI equals EF. All you're doing is replacing MGH with QV. Some of you are going to skip that whole analogy. Some of you are going to try to go straight to electricity and EI equals EF, and some of you are going to get it correct as a result of doing that. Great. Some of you are going to skip the analogy and get it wrong. If you end up getting it wrong, then that tells you that you made a mistake. Not that you made a mistake in the answer, but that you should have taken my advice, which is think of it as the car going down the hill or the car going up the hill, because we can see that. All right, here's a question. It's 572. It says 2 vertical parallel plates are connected to a DC power supply. Hey, listen, they draw the picture here, but they don't really need to draw the picture. We could do this without the picture. Vertical plates, I don't care whether they're vertical, horizontal, or diagonal. It doesn't make any difference. With gravity, we're always speeding up as we go downhill and slowing down as we go uphill, right? But with electricity, it's not affected by gravity. So it can be speeding up, going left, going right, going up, going down. It's affected by which way the electric field is. So the potential difference between those plates is 2,000 volts. Here's a sphere of mass, 3 times 10 to the minus 15, with a positive charge of 2.6 times 10 to the minus 12. It's placed at the positive plate and it's released. What happens, forget about what the question's asking right now, what happens when this positive particle is released from this positive plate? It speeds up because it's repelled by this and it's attracted to this, right? It speeds up. Right away, I start thinking, hey, that's like a car going down a hill. So right away, I start thinking EI equals EF. Let's read the rest of the question here. What's the speed of the sphere at the instant before it strikes the negative plate? Hey, wait, before it strikes the negative plate? Isn't that like saying what's the speed of the car the instant before it gets to the bottom of the hill? It's exactly like that. We're going to say EI equals EF. It says this mass is placed at the positive plate and released. So presumably it's not moving at the beginning, right? Car, picture this. No one, you picturing this? Picturing the car at the top of the hill? No one, what color is the car? Orange. Is it the General Lee? Does it have an 01 on the side of it? With a Confederate flag on the top? Yeah, okay. General Lee? Duke's a Hazard? Is Bo and Duke in the car? Um, is the car dirty or is it clean? Can you see it? Can you see the car right now? Pretty clean? Okay. Are the headlights on or not? No? Okay. So the floodlights are on? Okay. So this car is at the top of the hill. It's at rest. What kind of energy does it generally have at the top of the car, at the top of the hill? Is it sitting there at the top of the hill? Yeah, okay. So that generally has potential energy at the top of the hill. It doesn't have kinetic because it's not moving, right? When it reaches here's it generally at the top of the hill. When it generally reaches the bottom of the hill, when it reaches the bottom of the hill, what kind of energy does this car have now? Okay? When the cars reach the bottom of the hill, it has what? Kinetic energy, yeah. Now, what are we going to do with this? Well, let's make a little substitution here. What are we going to replace MGH with? How come? How come QV or VQ, as somebody said? Because we're not talking about gravity. We're just visualizing it that way, right? This has got electric potential energy. What do we want to find here? V? Yeah. So what do we got here? A charge of 2.6 times 10 to the minus 12 times VI is not initial speed, initial potential. Oh, wait a sec. It says my potential, should actually say potential difference between the plates. If the potential difference is 2,000 and the final potential is 0, then the initial potential will be the same as the potential difference. So we're going to say VI is 2,000. The final potential is 0 because we reached the bottom of the hill. Mass here, 3 times 10 to the minus 15 times VF squared. I do that, I end up getting 1862. What, is that right? No? That's what you got? One 1.9 times 10 to the 3 meters per second, 1900 meters per second? Yeah, I will, yeah. All right, here's what I'd like you to do. We've got 9 minutes left. You shouldn't have too much issue, I don't think, finishing up the 2 questions that go along with this on page 572. If you finish these up, some good practice questions for you to work on would be on worksheet number 9. All of them are good, but I'm suggesting worksheet number 9, number 1 to 3, and 6 and 7. These 2 questions must be done for tomorrow. I would suggest doing a few of these as practice, but I do understand, I'm conscious of the fact that you have an assignment due tomorrow as well, so I'm not assigning those questions as formal homework. Just the first 2.